Okay, so now we're going to look at some examples of the exponential family. So one of them is the Gaussian distribution. So the Gaussian distribution with mean mu and variance sigma squared, right, has the following probability density function. Okay, so P of x, and it depends parametrically on mu and sigma. Okay, so it's 1 over square root of 2 pi sigma times the exponential of x minus mu whole thing squared divided by 2 sigma squared with a minus sign. Okay, so let's consider what the random variables are. So consider the random variables. So let's have a random vector x, which is x1 and x2. And x1 is some function h1 of x, which is x squared, sorry, x. And x2 is h2 of x, which is x squared. Okay, so note that x and x squared are dependent. As random variables, right? But they are linearly independent functions. So, and the reason it's like why we've introduced h1 and h2, if you recall, is because we want to write the Gaussian distribution in the form of a member of the exponential family of distributions, right? Okay, so all right, so so these are the functions which are used in the definition. It's like of the exponential family, and then we have the variables, right? With the parameters. Sorry. Okay, so so the new parameters as follows are theta superscript 1 is mu divided by sigma squared, and sigma 2 is minus 1 over 2 sigma squared. Okay, and the reason to choose these things that way is that then this probability density function, then the PDF star can be written as P of x theta is the exponential of theta dot x minus some normalization factor which depends on theta, right? Okay, and so if you recall, it's like we choose this. Sorry, that's not it. Right. So yeah, so that is the normalization factor. I'm sorry. Yeah. Okay. So the normalization factor is given by so this is a convex function, if you recall, right? So this is given by the following. So it's mu squared divided by 2 sigma squared plus the log of square root of 2 pi times sigma. Okay, so I'm going to write it in terms of sigma 1 and sigma 2. Okay, so the minus sigma 1 squared divided by 4 sigma, sorry, theta 2, sorry, theta 1 and theta 2. Yep. Minus 1 over 2 log minus theta 2 plus 1/2 log pi. Okay. So, yeah, so as variables, these things are dependent, right? So we know that x1 and x2 are not independent. But they satisfy the relationship. X2 is equal to x1 squared. Okay. So what you want to do then is that you want to endow, it's like the space of x1 comma x2, it's like with measure, which imposes the relationship that x1 squared is equal to x2. Okay. So so to enforce this condition, right, we introduce a measure as follows, which basically concentrates the distribution on the set of x1, x2, which satisfy this relationship. Okay, so if you might have heard of the Dirac delta function, it's like, and so we're going to use the Dirac delta function in defining this measure. Okay, so d mu of x is equal to the Dirac delta x2 minus x1 squared. So it concentrates the measure on this set of pairs of points x1, x2 satisfying this relationship. Okay. All right. So where, again, delta is the delta function of Dirac delta. All right. Okay. So that's what we need to think of the Gaussian distribution. It's like as a member of the exponential family. Okay. Then the dual affine coordinates eta in terms of the expectations, right, given by the following. So eta 1 is right. So it's the expectation of x, basically. That's mu. And eta 2 is the expectation of x squared. That's mu squared plus sigma squared. Okay. All right, so anyway, so this is one way to think about the Gaussian distributions as being elements of this exponential family. All right, so we've specified the functions h1 and h2. We use specified phi, it's like, which is this convex function, which is used to normalize, it's like the distribution. We've introduced this measure, it's like which concentrates the distribution so that the constraint that x1 squared is equal to x2 is satisfied. And then we've looked at the the dual coordinates, which are expressed in terms of the expectation of x and x squared, which are given as follows. Okay? All right, so let me stop here for now.